Our next unit is called Roots and Powers, and we start off with looking at our number families. And every number can be placed into a specific number family, and then some numbers are in multiple number families, which we'll see with a diagram. Now, the first set of numbers that comes up are the natural numbers, and they're called the natural numbers because they were the first numbers people thought of naturally. Because the first place that numbers came into place was when you wanted to try to count something. And so you started counting with your fingers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And all the numbers that you could count with fit into the natural numbers. Now, the symbol for natural numbers, if there's actually a fancy one, if you're writing it out, sort of add an extra line to your n for your natural numbers. And you'll see that we'll do this with all the numbers. So the natural numbers came up first, and then, you know, someone would say, how many bananas do you have? I have 5 bananas. How many bananas do you have? I have 3 bananas. And then all of a sudden, someone was hungry, and they said, how many bananas do you have? And they didn't know how to answer it, because they ate them all. So that said, there became an important thing of introducing the number 0. And we see historically, we can see some cultures that invented a number for 0 and some cultures that didn't. And for those cultures that didn't invent a number for 0, their counting got very complicated. Right? Roman numerals. They didn't have a number for 0. They just kept adding new letters. Right? We've got I, and then V, and then X. And what's the next one? C. Well, M is 1,000, C is 100. There's one for 50. L is for 50. Right? They have a number for 500. D. And then after you get to M, like you just keep adding letters, and things got complicated, and the numbers got complicated. And so how do we introduce a 0? Well, that allows us to write numbers using we only have 10 symbols that we need to write any number. The numbers 1 through 9 plus 0. Okay? And then that person who was hungry and ate all their bananas all of a sudden said, can I have 2 of your bananas? And you say, yeah, but you'll have to give them back. So you take the 2 bananas. They ate those ones as well. And now we have an idea. I owe you 2 bananas. So how many bananas do you have? You technically have -2 because you owe somebody else bananas. And so those we have as our integers. And we're going to start already using the international symbol for integers, which is the Z with 2 lines. It comes from the German word for number, Zahlen. Yes?
So is the only difference between neutral and whole?
Is the 0.
So that's it?
That's the only thing different.
Okay.
So the number 3 is a natural number. It's a whole number. It's an integer. It's in a lot of families. The smallest family it would be is the natural numbers. And then we have our rational numbers where the symbol is a Q. And you think quotient because a rational number is any number that can be expressed as a fraction of integers. So it includes positive and negative. Any decimal that terminates or repeats can be written as a fraction. Do you know the way to write a repeating decimal? Okay, first of all, a decimal that terminates. Tell me when to stop. Oh my goodness. Stop. Okay. Write that as a fraction. You should have said stop earlier. How would you write that as a fraction? Over Now, when you write a decimal, this is, I mean, you should have said stop earlier. If I had written 0.32, you could write that as, oh, let's do 37, just for fun. you could write that as 37 over 100. And so when in our decimal points, these are tenths, these are hundredths. Of course, on this one, you went tenths, hundredths, thousands, 10,000s, 100,000s, millions, 10 millionths, 100 millionths. And if we're sure enough, we have 100 million on the bottom of our fraction. So any decimal that ends, you can always write it over a power of 10 and have a fraction. Do you know how to write repeating decimals as fractions? So let's start with an easy one. 0.4 repeated. What is that as a fraction? 4 over 9. If you had 0.32 repeated, what's that as a fraction? 32 over 99. And if you had 0.2481 repeated, I skipped a decimal just to see if you can see the pattern.
Grade 10s, M through Z, who have picture packages and wish to get a retake, please proceed to the library.
Will be 2481 over 9999. Cool. And so anything that repeats can be written as a fraction. So your rational numbers are all numbers that can be written as a fraction. They include your whole numbers. Could you write 5 as a fraction? It is 5 over 1. Yes, you could. Question? Why do we write it over 9? Well, that's just a pattern that occurs when you have a repeating decimal. I mean, if it's over 10, okay, if it's over 10, then it would end and terminate like it is. So one of the things that you can maybe see is if you took 1 and divided it into 3 things, 1/3, that's probably the smallest number that has a repeating decimal, it's 0.33 repeated. If you add up 3 of those, you get 1. And so you need the repeating decimals because you need to keep adding up as you go along to get closer and closer and closer and closer and closer to 1. And it always works out that any repeating decimal can be written over 9. Even this one, 1/3, is the same as 3 over 9. So it's just a neat pattern that occurs for all repeating decimals. Mathematically, why does that happen? I'll think of a good answer for that. The next set of numbers are all the numbers that you can't write as fractions. Sometimes, like this is probably the most common way, with a bar over top. Sometimes you'll see it with a squiggle in front. Sometimes you'll see it with a dash afterwards. It basically means not a rational number. Irrational numbers are all numbers that cannot be written as fractions. Whew. Now, these are decimals that never end and never repeat themselves. There are some special numbers, like pi is a special irrational number. I don't know, have you ever heard of the number e?
Isn't it used in banks to like study for interest?
For interest rates, yes. Okay, it's used a lot in calculus, and you'll learn more about it next year. But it's another special number. The video. And we can draw a diagram to show all of our number systems. So the reason that the circles are inside of each other is because all of the natural numbers are included in all of the whole numbers. And all of the whole numbers are included in all of the integers, which we should symbol with z just to get used to it. All of the integers can be written as fractions. And everything together, the rational numbers and the irrational numbers, make up the real number system which we deal with. And we don't go into the imaginary or the complex number system.
Why are the irrational numbers represented by a cube?
Because the word quotient, as in writing a fraction, something divided by something. And because they saved r for the real numbers, perhaps. Okay, so on the next page, we have some categorizing. You just need to put a Q or a Q with a bar over top of beside each one to check which is which. How did you do? 3/4 rational. Root 2 irrational. That one is a decimal that terminates, so it's rational. Pi is irrational. 4/9 is a fraction. Square root of 4 is equal to 2, which is a rational number. This one has no pattern and continues forever. So based on that, we would say that it's irrational. This one does have a pattern that repeats itself. So based on that, we would say that one is rational. In the next one, natural numbers, whole numbers, integers, rational numbers.
Do we want to apply like as many?
Irrational numbers, and yes, you want to apply as many of them as possible. So some of them will have lots, some of them will have few. And again, I'll give you a quick head start. One of the things that I do to figure these out is I try to think what's the smallest family it belongs to. So I've sort of listed my families from the smallest family to the biggest one. Is 44 a natural number? Yes. So as soon as it's a natural number, that means it's also a whole number, also an integer, and also a rational number. It will not be an irrational number. The irrational numbers are the ones that are completely separate, but it will also be a real number. So there's 5 families for 44. Is -3 a natural number? No. Is it a whole number? No. Is it an integer? Yes. So we've got integer, which means we also have rational number and real number. 0, natural number? No. Whole number? Yes. So we have whole number, integer, rational number, real number. Wuziker. Is that easier to remember if I pronounce them? Nuziker, Zucker, and Wuziker. No? 5/9. Not a natural number, not a whole number, not an integer, but it is a fraction. And finally, this decimal doesn't repeat itself, so it's irrational, but still a real number. And -2.3, It's not an integer, but it is a terminating decimal. I'm going to leave you the next question to do on your own, and you have some homework there.